Good afternoon or good morning or good evening, everyone. Welcome to the Blue Economy CRC's webinar series. I'm Professor Irene Pennesis, the Research Director at the Blue Economy CRC. Firstly, on behalf of the Blue Economy CRC, I'd like to begin by acknowledging the traditional owners of the land on which we are hosting this webinar today. I would like to pay my respects to the elders past and present and the Aboriginal and Torres Strait Islander people. The Blue Economy CRC was established with a 10-year life under the Australian Government's CRC program back in July 2019. Now with 44 partners from Australia and around the globe, the purpose of the CRC is to perform world-class collaborative industry-focused research and training that underpins the growth of the blue economy through increased offshore aquaculture production and increased offshore renewable energy production. Today, we have a very exciting webinar, and I'm very excited to bring this webinar because it's a topic that's very dear to me around ocean energy, and it's about a framework for evaluating and guiding ocean energy technology developments, and it's really a presentation of the Ocean Energy Systems, which is one of the technology collaboration programs under the International Energy Agency. It's a framework that's been produced, and actually today we're going to take a look at the framework. We're going to learn a little bit more about the IEA OES Technology Collaboration Program, learn more about the framework and its application, and we're going to actually do that with a special presentation from Carnegie Clean Energy as well. So the International Energy Agency, just very briefly, is a technology collaboration program, and they published an international evaluation and guideline framework for ocean energy technology. The document is there and intended to support international efforts by presenting a framework for technology evaluation and guidance of engineering activity, ensuring that decision makers have consistent information available to them. Today, our guest speakers will be three. It will be, and I'll work, of course, from the first presentation, which I'll provide, which is a bit of information about the IEA OES Technology Collaboration Program, to give people some understanding of how that program is funded by our membership by the Australian Government, the Department of Climate Change, Energy, the Environment and Water. The objectives and content and benefits of the evaluation guidance framework and experience of national and international funders in its adoption is going to be presented by Dr. Jonathan Hodges. He's the Innovation and Strategy Manager at Wave Energy Scotland, and a colleague that I've known for quite some time, doing some really excellent work at Wave Energy Scotland in the development of different ocean energy technologies, but also in relation to offshore wind developments as well. And then we're going to have a presentation actually on the application of the framework in the development of Carnegie Clean Energy's CETO technology towards commercialisation as part of their project in the Europe Wave program. And only recently, in the last couple of months, Carnegie Clean Energy was announced as one of the successful projects to move into phase 3 of the Europe Wave PCP program. After these three presentations, we're going to have a Q&A, and we will be able to address all your questions in the Q&A box on your screen. So please do provide us your questions. And if there's any popular questions, we might take those first, move them to the top of the list. Please make sure you do that too by clicking which ones you want to hear from. And we'll try and answer some of them as well in the chat for those that we don't get to answer live today in the webinar. So I'm going to start now with the presentation just to tell you a little bit more about ocean energy systems. So this is one of the International Energy Agency's collaboration programs. I am the research director in the CRC, but I'm actually the Australian delegate for IEA OES. And so I play that role again with an alternate delegate, which I'll introduce you to. Ocean Energy Systems, well, we call it OES in the short form, but it's one of the collaboration programs. It's an international collaboration between countries founded back in 2001, which operates under a framework established by the International Energy Agency in Paris. So just to let you know a little bit about who the delegates are in Australia, in case you ever want to reach out to us and ask us more questions about our activities in the OES. So I'm the primary delegate from the Blue Economy CRC, and we manage our engagement with the OES and the IEA. And then Professor Christophe Gaudin is the alternate delegate for Australia. He's based at the University of Western Australia. He's a director of the Marine Energy Research Australia Centre, and he's also a vice co-chair of the OES Executive Committee, which is the cabinet that leads the OES as well. So established in 1974, the IEA carries out a comprehensive program on energy cooperation for 29 member countries. And beyond that, really, in examining the spectrum of all energy issues and advocating for policies that will enhance energy security, look at economic development, the environment and awareness around the environment and engagement worldwide. So they have a number of activities that they've actually set up. And these are called technology collaboration programs, and you can see them on your screen at the moment. We're going to be talking a lot today about ocean energy, but in the renewable energy space, there's ones on photovoltaics, hydropower, geothermal energy, bioenergy, and also wind energy, which also covers offshore wind. These are independent bodies operating in the framework provided by the IEA. There are 42 active technology collaboration programs, and of course, we belong to the OES. And we probably engage around 6,000 experts participating from different government and international bodies that are interested, of course, in ocean energy. So for those who probably don't have a very, very clear background, you know, oceans are the world's largest untapped source of energy. Ocean energy technologies exploit the power of tides and waves, as well as the difference in temperature and salinity to produce energy. And so the IEA OES embraces the full range of ocean energy technologies. You know, this has been a major program in other countries in the world, with international engagement from a number of different government departments, electrical utilities, government agencies and energy agencies, a number of research organisations, universities and industry associations. So really it spans a number of experts nationally and internationally who have capacity to help inform ocean energy developments. You may not know this, but you know, Europe are very committed to targets in ocean energy, and Jonathan Hodges can tell us more about that if you have a question about that. And you know, they've stated actually that 10% of Europe's current electricity needs by 2050 could come from ocean energy. Here in Australia, we currently don't have any installed ocean energy technologies. The Blue Economy CRC and other organisations in Australia are developing these type of technologies, but we know that our wave energy alone surpasses all of Australians' current electricity needs and is one of the most globally recognised resources in the world in ocean energy. So OES really covers all these forms of energy in the sea and through the motive power, through physical and chemical properties. It doesn't represent offshore wind generation since seawater isn't the motive energy here, but that is covered under the Wind Energy Technology Initiative, which I mentioned to you earlier. Well, sorry about that. So what are some of the work programs that the OES is involved in? They have a number of different projects that you can see on the left-hand side. One of the more significant activities that's been happening has been around looking at the environmental effects and monitoring effects associated with the installation of ocean energy technologies. They've been doing a lot of economic analysis looking at the cost of wave, tidal and OTEC. Today we're going to hear from Jonathan about the second edition of the International Evaluation Framework for Ocean Energy, which was only released a couple of weeks ago. And of course, you know, ocean energy is a form of energy that can be used in a number of different alternate markets, of course, and the blue economy is one of those markets which we've been looking at, of course, to help decarbonise activities like aquaculture or other maritime activities. And then, of course, in very recent times, there's been a development of an international vision for ocean energy, and that will actually be released as a report very, very shortly by the IEA. There are a number of working groups that are working on wave and tidal energy, looking at numerical modelling, trying to look at best practice. And in addition, there are a number of databases, worldwide databases, that provide information about ocean energy projects that are happening all around the world. And I really recommend that you take a look at some of those to learn more about that, and also some of the international water test sites actually that are available for those who are developing technologies. So I want to just briefly speak about some of the really key activities that have been coming out of the OES recently. And this is probably one of the most significant reports that I've seen come from the OES, which is the State of the Science report. And this is a report that's looking at the environmental effects around marine renewable energy development around the world. So this is probably covering the most current and pertinent published information on the interactions of these devices and associated infrastructure in our marine environment. And it addresses really a lot of the environmental challenges associated with ocean energy developments, but it also actually takes us through retiring some of the risks associated with these developments that might be perceived by government or by industry or by investors. So this State of the Science report has 14 very detailed chapters with a lot of contributions to these reports and lots of scientists and engineers from many countries and around the world that have actually contributed. And you can find that report on the TEFAS website that's hosted by Pacific National Northwest Laboratories in the US. Another one, of course, that we are going to learn a lot more about today is around building consensus for technology evaluation. And so today we're going to hear from Jonathan about the second edition of the framework for evaluating and guiding ocean energy technology developments. But there's been other reports that have been published as well by the IEA that look at that technology development and commercialisation space, looking at specifically standards and certification. But this has been really an ambiguous process for the development and evaluation of these technologies to date. And really, we've needed appropriate guidance and robust activities through the development process to be able to assess these technologies. And really, this framework provides support for decision makers associated with evaluating these technologies and the funding allocation. And you can see from the figure on the right-hand side that we're talking about everything from concept creation right through to commercialisation and all those different stages that are covered. So this is really a great document for policy developers, decision makers, and other investors who want to de-risk investment and support decisions for ocean energy developments. So we're going to hear more from Jonathan about that. Another really important area that the Ocean Energy Systems has been looking at is alternative markets for ocean energy. And so ocean energy devices are designed to be installed in very large arrays to provide utility scale power due to the worldwide resource that I mentioned earlier. But they can actually also be tailored to meet energy and water needs for a number of different applications. And you can see from the reports that the OES has done that they've been looking at ocean energy linked to remote islands and communities and coastal communities. They've been looking at ocean energy that can be used directly for offshore industries. For example, aquaculture, marine macroalgae production, water supply through desalination, monitoring of oceanographic equipment and powering those oceanographic equipment, and even potentially security activities to do with defence. So probably the two most recent publications to bring your attention to, if we go with the first one, this is a report that was only recently published. It includes 5 interviews exploring the objective site selection and technical considerations and socioeconomic impacts and considerations for ocean energy projects on islands. So they've provided a comprehensive resource for those who are interested in the field of ocean energy, in particular to do with island and coastal communities. They feature some great projects and interviews. One of them is an Australian developer called, of course, in this case, which is Paul Gleeson, is the CEO of Waveswell, and they talk about their project on King Island, which was the Uniwave 200 project, where they were providing power to the microgrid on King Island in Tasmania. But there are other really great projects here looking at Nova Innovation, doing a tidal array in the Shetland Islands in the UK, Minestrone looking at their tidal kite at the Faroe Islands, Sabella looking at their project in France in Ushant, and then of course some river power systems in Alaska for providing ocean energy through rivers and tides. So really fantastic interviews, and they offer a lot of guidance and insight about future projects, the importance of acceptable technologies and community-driven approaches. And they also really provide a lot of knowledge about some of the success and failures that have happened through some of the projects that they've been through. So really educating others. The last one I'll turn your attention to is one that was led by the Australian, of course, Blue Economy CRC and the Pacific Northwest National Laboratory in the US, where we investigated the energy requirements for offshore aquaculture industry, and we considered the feasibility of co-locating offshore aquaculture with ocean renewable energy as a part of an effort to help decarbonise the industry, but also related to the activities of the blue economy. And look, we brought together a number of different nations who have interests in collaborating on aquaculture and ocean energy co-located, and really try to find that information and make it readily available to help sort of really expand the opportunities for decarbonising aquaculture through ocean energy, because it's really quite a good match. Only earlier this year, we published an annual report. The OES published an annual report. The annual report provides and showcases all of the activities that happened around the world in ocean energy during 2022. It highlights a lot of the key achievements and recent outcomes of the IEA OES and at a global scale. And as well as that, you know, it looks at all the ocean energy policy that's being developed internationally, the research, the advancements in different deployments in all the participating member countries in the OES. So I really highly recommend that you take a look at that annual report, and that's released every year around July. So the next one will be released for 2023 next year. But there are a number of other documents that are provided on the OES website, which I would recommend that you take a look at, really highlighting a lot of the activities that the OES is doing. So please, I recommend that you go to the website and take a look. So now I'm going to pause and introduce Jonathan Hodges. So I will just stop sharing and give Jonathan time to share his slides.
Good morning, good afternoon. I'll just share my slides. Thank you, Irene.
Thank you, Jonathan. I'm going to just provide a very quick introduction about you, if that's okay.
That'd be lovely, thank you.
Really appreciate the opportunity for you to come and present. I know that for Jonathan at the moment, it is 5 a.m. in Scotland, so we have to thank him for his opportunity to come and present in this webinar today. And this is really important because Jonathan's been talking to a lot of developers, a lot of policymakers, a lot of investors about this framework and how it can help other countries guide their developments. Jonathan is someone that, you know, I've known for quite some time and engaged with. And look, Jonathan's going to really talk to us a lot about that framework. He's followed a very long career actually in the aerospace industry to begin with, developing and testing Rolls-Royce turbofan engines. He then moved to the ocean energy sector, where he gathered innovation, resource assessment, technical economic analysis experience. And now in his role as innovation and strategic manager at Wave Energy Scotland, he aims to identify innovative opportunities, influence research agendas, and develop funding strategies to help the sector deliver cost-competitive wave energy technologies. So we're really pleased to have Jonathan here today. Jonathan, thank you so much. I'll pass it over to you.
Thank you very much for that kind introduction, and good morning, good afternoon, everybody. Irene, thanks so much for the invitation to speak on this webinar. It's lovely to be able to speak to you from Scotland this morning, and really nice to be able to speak alongside Alex from Carnegie Clean Energy, who I think is going to have a really interesting perspective on the topic we're talking about today. So I want to start off by telling you a little bit about Wave Energy Scotland so that you know how I've got into this topic of stage gate metrics. Then I'll move on to an OES presentation to talk to you about the task that Irene introduced just now. I'll talk to you through the various publications that we've made out of this activity, which hopefully you've seen some of them, resulting recently in the publication of the second edition of the OES Evaluation and Guidance Framework. And then I want to spend a lot of the time talking about the adoption of the framework and its recommendations and the benefits that it seems to be bringing to various people around the world of various different types. And all of the work that I'm sharing with you this morning has been delivered through a long series of stakeholder engagements, but primarily by this working group, the logos you can see on the right. So members of the OES, Wave Energy Scotland, European Commission, Technalia, the Research Alliance in the Basque Country in Spain, members of the Water Power Technologies Office at the US Department of Energy, US University of Edinburgh, and the Sustainable Energy Authority of Ireland, alongside various workshops through the years, since starting in 2015 even, involving public funders, private investors, technology developers, and researchers. So it's been a thorough process of technology understanding and engagement with various stakeholders. So I'll start off just to give you some background about Wave Energy Scotland, which might be new to many of you. So Scotland has a very long history of technology development in wave energy, and Wave Energy Scotland was set up at the request of the Scottish Government in 2014, and that was quite a difficult time in the sector in Scotland. Two of the famous technology developers, which you might know, Pelamis and Aquamarine Power, had just gone into administration, and it was a really challenging time where there was a lot of IP that was at risk, and the Scottish Government wanted to maintain what was a leading position in development of this technology. So they set up Wave Energy Scotland, and we were tasked with the key objective of developing cost competitive wave energy technology. And we've been doing that ever since through a competitive research and innovation program that focused on what we consider to be the 5 key areas of technology within wave energy. So power takeoffs, wave energy devices themselves, control systems, structural materials, and quick connection and mooring systems. And through that program, we've funded 132 projects, committed over £50 million, and worked with more than 300 organisations all over the world from more than 18 countries now. So that's the Wave Energy Scotland programme, just to give you a feel for what it looks like, which will become familiar as we talk more about the framework. It's all about a stage-gated competitive programme. So each of the 5 programmes that I just mentioned, each go through 3 stages with a large number of technologies developed in stage 1, competition against each other to move to stage 2 through a stage gate, and then stage 3 with increasing funding and quite specific activities required in each stage. And you'll just see the mention here of Europe Wave at the bottom, which we'll talk about in much more detail in a while. So it's that competitive program, performance metrics and stage gate metrics, and the ability to make decisions at the stage gate is really what we're talking about here today. So just to give you a feel for what's come out of the program, all the way from concept development, early stage tank testing and flume testing of concepts on the left. These are the 2 technologies which have come all the way through the Wave Energy device program, through from concept development, large scale demonstration and proof of concept testing in the waters of Orkney in northern Scotland. At the top, Motion Energy, and at the bottom, AWS Ocean Energy. So those are the 2 headline technologies, and inside those technologies and available for future application, there's a lot of enabling and supporting technologies that have come through the other programs that we've run. And our activities now are to support those technologies of where they go next. So commercialization, and a lot of focus at the moment on co-location that Irene just mentioned, particularly co-location of wind devices, floating wind devices, as wind technologies go into much deeper water around Scotland and into much higher wave resources. We're looking at opportunities for co-locating and sharing of services, supply chain, and infrastructure, including platforms. So that's the Wave Energy Scotland background. Now I'll move on to an OES presentation. I became first involved in the task of the OES maybe 2017, 18, and then have been leading it ever since. And it's a task to develop, share, and help embed the concept of stage gate metrics and performance metrics into the ocean energy sector. And it focuses on tidal stream and wave. Although I understand the task may be expanded into other ocean energy sources, but particularly wave and tidal, the ones that are benefiting from it so far. So first of all, target users. I'll tell you about the publications we made, but the target users of the whole piece of the whole activity are primarily public funders. But then we've come to understand through the engagement process and through the feedback of the adoption of the documents that technology developers and private investors are also finding real benefit in its recommendations. So remember that it's primarily aimed at public funders. In terms of objectives, with us hoping to support a stage-gated approach to technology development, we really want the recommendations of this framework to be able to support public funders' decision making, make sure they can make the most efficient use of public funds, and by doing so, accelerate technology development. And the outcome of that is the documents that we'll speak about today, the International Evaluation and Guidance Framework for Ocean Energy Technologies from OES. And to summarize at the highest level the content of that and the real benefits of it, one is common language. That's quite a simple thing, but quite beneficial for both funders and technology developers to be able to understand what are the requirements of a funding program, and behind that, what are the requirements of a successful technology. So being able to speak the same language really helps with the application process in a funding program and evaluation. Stages and stage activities, and evaluation areas and evaluation criteria. So I'll describe those things in more detail. So publications, we published the first edition of the framework in 2021 and carried out a series of activities over the years to promote that, primarily to public funders, but also to the other users as well. During that process, we found that one of the big questions was, how does this relate to the IEC framework, the International Electrotechnical Committee? How do our recommendations align with their technical standards, technical specifications? So in the second document you can see there, we illustrated exactly how those two sets of guidance align with each other, and also the IEC RE and other sources of guidance available in the sector. And I worked with Jonathan Colby from the IEC to deliver that. Then we were promoting the framework to national governments and national funders around the world. And to support with that, we published a series of 4 translations of a very brief introduction in English, Chinese, Spanish, and French to help people from the OES mainly present the framework back to funders in their countries and promote adoption in that way. And then, based on the feedback that we'd received, we recently published a second edition with a couple of extra additions. So what does the document contain? The main content of the document, as I said, was a set of stages, a set of evaluation areas. So the stages you can see in the middle, from stage 0 of concept creation, all the way through concept development, optimization, scaled demonstration, all the way up to commercial scale, and then commercial scale array demonstration. Now, from our experience in Wave Energy Scotland, our program covers stages 1, 2, and 3. But as you can see, our objectives are to carry out development all the way to a commercial project and a product. Through a lot of the work I've done at Wave Energy Scotland over the years has all been about very early stage concept creation as well. So we added on, in alignment with a similar set of stages from the IEC, concept creation, because a lot of decisions that are made at the very, very early stages can really influence your ability to deliver good results against the evaluation areas that you can see on the right. So the evaluation areas are the key areas of technical performance and the key areas of technical characteristics that a successful ocean energy technology needs to be able to deliver. And in the first edition of the framework, we had 9 of these evaluation areas. And in the second edition, we added environmental acceptability, which was one of the key pieces of feedback that we received during the first couple of years of adoption. What about environmental acceptability? So the first 9, power capture, power conversion, survivability, maintainability, to name a few, all focused into the key requirement of affordability. And the framework illustrates the hierarchy of these evaluation areas and gives a clear definition of each of them. And I mentioned common language at the beginning. Even that has been a real benefit to the relationship between funders and technology developers, because often a funder will ask someone to demonstrate reliability or survivability, and technology developers have often asked, what do you mean by that? So they can immediately point to a very brief 2 or 3 line definition of that word. And then immediately the two are speaking the same language and able to respond to technology developers, are able to respond to questions in evaluations. So that common language already becomes beneficial. Then in the second edition, we added environmental acceptability, and we're very clear that we have a limited remit here. There is another activity within the OES called OES Environmental, and that's the real source of knowledge and guidance and expertise in environmental impact, environmental implications of these technologies. What we try to add in this document is the link for guiding technology development to be more environmentally acceptable, and what characteristics you need to deliver, what high-level processes need to be considered, and again, how that is really important to consider at stage 0. Big decisions can be made there. So in the framework, for each stage and for each evaluation area, the guidance gives a set of stage activities, and a lot of that comes from experience of the Wave Energy Scotland programme and input from many other technology developers and funders around the world. A set of engineering activities that are expected at each stage, and we'll talk about the benefits of that later. And then for each stage and each evaluation area, we have some evaluation criteria, and those are the technical parameters that people should be able to present their results in to be able to demonstrate progress. And as I mentioned, in the second edition, we added some clarity on how this guidance aligns with other complementary sources of guidance, such as the IEC standards. So adoption. We've had a lot of adoption from public funders around the world. The most active adopters have probably been us in Wave Energy Scotland, the European Commission, the Water Power Technologies Office, the Basque Energy Agency in Spain, and SEAI, the Sustainable Energy Authority of Ireland. But we've received different levels of feedback from many other public funders and technology developers around the world. So that led us to kind of classify what type of adoption we had experienced. And I think that's most easily summarized with this diagram on the left. Active funder adoption, where people actively use the framework to guide their programs. Then passive funder adoption, which is quite simple but also brings significant benefits. And then developer adoption. And those three parties have quite different relationships with the guidance framework. So I was going to talk briefly about each of those and how they've experienced benefits. So first of all, active funder adoption. The benefits that some funders have found, and particularly in the United States and in the European Commission, is the ability to directly use the recommendations of the framework. So the stages, the evaluation areas, and the stage activities to say, this is what we want you to do in our funding program, and design the stages of a funding program and the expectations of that funding program. We found that funders have experienced a real benefit from the clear expectations that they can provide to applicants of what is your technology background, what should you have done to be eligible for this stage of a funding program, what's the expectation of data and outcomes at the end of that stage, at the end of the project, the key areas of technology attractiveness that a project should focus on, and then again, that definitions and common language so that people can both present their outcomes clearly and use the right language to do so. In a program of different projects to be funded, it's really beneficial to be able to evaluate and compare technologies against each other at a stage gate using a consistent data set, and everybody working to a similar set of expectations really helps with that. And it also is extremely valuable for a funder to be able to monitor and report progress up to government and up to different external stakeholders to say, this is the impact of the public funding, this is where we've taken the technology from and to, and this is the improvement in that technology that we've been able to demonstrate. And within that, risks and impacts, the ability to be able to identify risk at an early stage in a project, limit that exposure to risk for a public funder into stages, and then be able to manage that risk through a program has been one of the most significant benefits. Comparing this to previous funding opportunities, particularly in Scotland, speaking from my own experience, large grant projects being delivered to a small number of companies with a lesser ability for government to be able to manage that process and manage the exposure to risk and manage the impacts of that. That's a really significant benefit that we've experienced of breaking things down into stages and having clear expectations. So that's the active adopter. And as I mentioned, there's been a series of adopters around the world, and these are the most notable ones. And I want to talk a little bit more, when I talk about active adoption, about Wave Energy Scotland, the Ente Vasco de la Energia in the Basque Energy Agency, and a program that they've worked on called Europe Wave, which is going to link nicely into Alex's activities at Carnegie Clean Energy. A project called Europe Wave, which is effectively a European level version of a stage-gated technology development program for wave energy. So I'm just going to show a few slides from one of my colleagues who helps to run the Europe Wave program. So they have developed a 3-stage program based entirely on the recommendations of the framework. So they taken guidance from the stages, the evaluation areas, and on the right, an example of the stage activities, and designed a funding program based upon that. The Europe Wave program takes in stages 2 and 3 of the OES framework, so the mid-level TRLs, and running from 2021 to 2026. And we're working to support the next stages of technology development, as I mentioned. I just mentioned TRL there, technology readiness levels, and that's one of the key things that drove us to produce this guidance. Is a lot of funding programs are based around TRLs, and that's a useful measure of maturity of technology development, but it's also can be quite a dangerous thing for comparing technologies and being able to present progress. It's relatively easy to be able to achieve a TRL, but have you achieved that TRL with the right background, with the right demonstration of performance, and are you demonstrating a quality technology? The difference between a TRL and an attractive technology can be quite different sometimes. So the ability to combine these mid TRLs 3 to 6 with a demonstration of what stage you have achieved and what performance outputs, data outputs you're presenting is a real improvement. So just very quickly, if you look at the Europe Wave program across 3 stages, the team were able to take the OES guidance framework and add in all of the other activities that they wanted to see based upon the stage activities in the framework. So all from design through to financial and management. What is expected out of each stage of or phase in their language of the Europe Wave program. And again, stage 1, concept development, stage 2 or phase 2, design and modeling, up to phase 3, OpenSea deployment and testing, which is the phase we're just starting now. And you can see at the bottom, completion of stage 2 of the IEA framework, completion of stage 3 of the IEA framework. So it's directly using the expectations of the framework in the evaluation at the end of each stage. So that's active adopter. Let's just talk a little bit about the other forms of adoption that we've experienced: passive funder adoption and developer adoption. The benefits that people have experienced who aren't public funders are the other side of that relationship with a clear language, being able to understand the funder's expectations with the clear language, build a clear narrative of your technology development path, where you've come from and where you're going to, being able to demonstrate technology performance using the right criteria against the right evaluation areas, use that common language and data. And more than anything, it's very, very easy to adopt. And an example of that is, here's some text which is quite small, I apologize, but these are extracts from a European Commission funding program. One of the pieces of feedback I received from some public funders is there's real benefit in this document, in this guidance, but we don't have a wave energy funding program, or we don't have a tidal energy funding program. We just have a generic renewable energy funding program, so we can't apply the recommendations. So what we've experienced there is that just by including some text, for example, this highlighted on the right, in the call guidance text, a techno-economic analysis should be included, including key performance indicators based on an internationally recognized set of metrics. Just by including some text like that, you can highlight that to wave and tidal applicants that you support the use of this framework. And we've really experienced improved quality of proposals by funders using the guidance. So we experience receiving proposals, even when not required, all laid out against the topics, against the key expectations, using the right language, using the right criteria to demonstrate progress and methodology. So even just by supporting the use of the framework, you will get improved applications into the wave and tidal component of your program. So very easy to adopt or to get some benefit. The other side of it is developer adoption, which has been a really significant component of the feedback that we received actually, and led to the questions that I mentioned earlier about how does this align with IEC. So as I said, I worked with Jonathan Colby from the IEC to help make it clear how these sets of guidance align with each other. So going all the way through from the OES framework through IEC standards, certification bodies and test laboratories, and finally the IEC RE system. And this is the way they fit together. So the IEA OES framework is all about driving innovation, helping selection of quality technologies, prioritizing those through most efficient use of public funding, and as I said, ability to manage risk through those relatively early stage programs. So that's guiding funding programs and developers to say what should be done and what should be presented. Now, when you actually start to deliver the technical work, developers are much more interested in guidance that says how should that be done. So they're really interested in the IEC standards that say how you should develop something, how you should design it, how you should operate it, etc. So there's a really a nice relationship between the two, where the OES is primarily aimed at a public funder trying to guide technology development. These are the activities, these are the things that should be presented. And the IEC mirrors that, increasingly so, as more standards are developed to give technology developers clear guidance on how that should be done. And then that feeds on to the ability of certification bodies and test laboratories to carry out third-party verification, make sure people have adhered to those standards, de-risk the technology and ensure credibility, and then finally into conformity assessment and the international recognition of the IEC renewable energy system. So it's a nice chain where using relatively simple language and simple guidance, the OES framework feeds technology developers into this process, but also gives public funders, maybe not particularly technically minded public funders, a pathway and a view into this whole process. So it links the whole thing together. So developer adoption, quite beneficial there. So just to go back to the beginning, stage gate metrics, we've had some great experience of it in Scotland, and many other programs around the world have experienced the same thing. That led to our leadership of the OES task on performance metrics. We've had a series of publications and a lot of great adoption, a lot of feedback from that. What we find is that the wider the adoption of a set of guidance like this, the more value it has, and that increases the benefit to the sector. Particularly, I mentioned that it helps people to understand what the expectations of your pedigree of your technology before entering a stage of a program. If a technology moves from Australia to Europe to the United States, if everybody's adopted the same framework, then you can say, I delivered stage 1 under this Australian funding program, I delivered stage 2 under a United States funding program. And that's something we experience a lot, technology developers moving from country to country. And it really helps all of those public funders to have a clarity of understanding of what's been done before. And in the early stages of the WES program, we ran one program where you could enter into stage 1, 2, and 3, and everyone wanted to be in stage 3, but it wasn't the right thing for some of the technology developers and for the funder to fund people without the right experience. So guidance framework like this helps us to be able to say your technology development so far makes you ready for stage 2 or stage 1. And that was a good benefit to make sure that people get into the right stage of a funding program. As I mentioned, adoption is easy. It's easy for funders. If you wanted to adopt it relatively passively, you still get benefits in terms of improvements to proposals, a better quality of proposal, better quality of project. If you want to use it in more detail, more actively, then you can design a whole funding program around it. So we really hope that will continue to support technology development and technology funders to run good programs. And most importantly, feedback is always welcome. This is going to be reviewed on an annual cycle by the OES and potentially updated on a similar cadence. So feedback is always welcome, and my email address is on the back of the document. So please contact me if you've got any questions or any feedback on the document. It'd be great to hear from you. So that's all I wanted to say for now. I will pass back to Irene, and thanks for being there to listen this morning.
Thank you, Alex. I really appreciate. Thank you, Jonathan. I really appreciate that. I'm just going to turn my video back on. Thank you so much. You know, it's such an important framework, but there has been a question that's come up in the chat, and I thought maybe I could just go ahead and we can answer it live, given that it's the one question we've got. And I really would recommend people please pop their questions in the Q&A. But there's a question here that says that the technology evaluation areas seem to be really well thought out, but has there been some omission related to the power export integrity? So a number of the wave and tidal projects, tidal systems have experienced some failures when it comes to their power export systems, like the connectors, the dynamic risers, the export cables. Can you comment whether this has been omitted or whether it's captured somewhere else in the evaluation system?
It's an interesting question. That the boundary of how far this guidance should go has always been really interesting. To me, that's quite a technical topic which should be covered by IEC guidance. I think that the scope of this framework is intended to guide the development of wave and tidal devices, and I think in the document there's an illustration of all the different levels of a project through all a product all the way through to an installation and a project, and our scope is very much on the technology. So I think it's a really important topic, and I think it's alongside a lot of other technical projects that probably should be covered by IEC guidance.
Yeah, that's right. I think we should mention that there are a number of International Electrotechnical Commission standards and guidelines for the development of marine energy that industry uses, that covers everything from technology development and TRLs right through to exporting power.
Exactly, and we're going to be really closely working with the IEC to make sure that we build upon that link between these two documents. There's a matrix in the back that lines IEC guidance with the evaluation areas of this document, and there's lots of links between the two to guide technology developers. And I think that's part of the document that will get updated on a regular basis as more and more technical specifications are published by IEC.
Thank you, Jonathan. We really appreciate your presentation. What I'll do now is I'll go back to introducing Alex and introduce Alex now for his presentation. I'll give Alex a moment to actually share his screen as well. So Dr. Alex Pickard is the Chief Technology Officer at Carnegie Clean Energy, and they're a partner, of course, in the Blue Economy CRC. Formerly a systems engineer and data analyst at Carnegie Clean Energy, Alex is now leading the development of the technology at Carnegie. Alex has been working with the engineering team at Carnegie for 10 years and has acquired a lot of knowledge over that time around the CETO technology, and of course, around the wave energy industry in general, of course. He's contributed to the design, the construction, installation and operational phases of Carnegie's previous projects. The one in particular that we remember, of course, is back in 2018, 2019, of course, was the Perth Wave Energy Project. And then, of course, several other deployments of the CETO units as part of that at Garden Island. And he's very passionate about climate energy challenge, looking at innovative technical solutions, and he's happiest when he's, of course, on the ocean, free diving, kite surfing and exploring. So I think a lot of people who are into ocean energy share this as well. So Alex, thank you so much. I understand that today, you know, this is an opportunity for people to hear about from Jonathan the framework, but this is also about, as a technology developer, this framework has guided your developments under the Europe Wave program, as has been previously mentioned. And that's, you know, really driving some of the competitive investment into ocean energy technology development. And you've used this framework in the context of going through the different phases in the Europe Wave program. So I'd really love to invite you now to present about your technology development and how you've applied this framework so that people get a feel for how valuable this framework is in providing guidance around technology development and evaluation.
Thanks a lot, Irene, for the nice introduction. And thanks everyone for joining in today to talk about the OES-IEA framework. Thank you as well to Jonathan for the really nice presentation. It provides a great introduction for mine and allow me to go directly into the application without presenting the context, which Jonathan did a great job at. So yeah, I guess we're talking today about how we have applied this framework at Carnegie. But to begin with, I just want to introduce briefly the company I work for, Carnegie Clean Energy. So we are a wave energy technology developer based in Western Australia. We listed on the Australian Stock Exchange. We've got about 12,000 shareholders, and we have been developing a number of products, a number of technology. The one I'm going to talk mostly about today is the CETO technology. But we've also been focusing on the MoPower technology. I'll say a few words about that as well, the wave predictor and the mooring tensioners. So our expertise lies in the design, numerical simulation, testing, and offshore deployment of these technologies. And we've been doing that over the last 20 years. We're developing those technology, I guess, not in isolation, because we believe we can't succeed in this industry without a collaborative approach. So we're really trying to nurture, I guess, this ecosystem we're involving in, engaging in a lot of collaboration with both academia and the industry. And I guess one we often like to talk about is our collaboration with Hewlett-Packard Enterprise on the groundbreaking development of a reinforcement learning controller. I'll talk a little bit more about that as well in the next slide. But yeah, let's mention briefly one of the technology we're focusing on at the moment, which is the MoPower technology. This is a spin-off of the CETO technology. The concept was to reuse some of the components of the CETO technology to decarbonize some of the offshore activity that we observe. So the basic concept is the following. I guess the main application we're focusing on at the moment is aquaculture. And the main reason for that is we do have those large structure that the industry called feeding barge that are sitting next to the fish farm. And the main application of those is to provide to feed the fish during the time. So those are large structures that are located offshore in energetic environment, and that needs a fair amount of power, and that's currently only being provided by diesel generation. So the idea was, let's try to capture some of the motion of those structure to displace some of that diesel. So that's what we're doing with the MoPower technology. And again, I guess we've embarked in that development following a stage approach, similar to what Jonathan presented you before. So the first step along that way is to develop, is to complete the conceptual design, but then to develop and deploy and test a small scale prototype. So this is what we're currently doing with the support of the Blue Economy CRC. We're hoping to have the technology deployed in the next couple of months. And obviously the next step is to deploy the technology on the full-scale commercial vessel in partnership with our Blue Economy partner, Huon and Tassal, that are aquaculture industry partner. So the technology we're developing, which is the main topic of today, is called CITO. It's really dedicated at electricity production for utility scale market, and it's really optimized around capturing that energy. So wave energy devices are typically they have different types. So our technology is a point absorber type. It's also axisymmetric, which means we can capture energy coming from all directions. It's fully submerged, which reduces visual impact, which is an important aspect for some sites. It's multi-mode. You notice there is 3 mooring line, which means that we can capture actually all degrees of motion of the device. So it moves in heave, in surge, and we can capture all of those. It is fully scalable, so we can adjust the size to suit different sites, different wave period, and different energy demands, I guess. But it's also suitable for different depths. So, some sites have very different depth, and we can adapt to that by just simply changing the length of the mooring line. The whole design was really developed with LCOE in mind. So LCOE is levelized cost of energy. That's the cost of the energy you produce with your technology. It's typically in $ per megawatt hour. And I guess the whole design process have been keeping in mind, I guess, these metrics to make sure that every design decision we're making along the way leads to a better LCOE. And I guess that this ties into the evaluation criteria Jonathan mentioned before, which is affordability. Another important aspect of our technology is survivability. So we have a unique feature that allow us to survive those large storms. Only last week there was some very serious storm rolling through the west coast of Europe, with 18-meter wave being recorded. So when you deploy your technology in those sites, you need to be able to survive those events. And the unique feature of our technology is the ability to dive down, so we can increase the depth of the device to shelter it from those really energetic conditions that are close to the surface. And that's another, I guess, evaluation criteria, which is related to the reliability of your technology. So maybe to describe briefly the different components of the technology, you can notice this big green buoy, which is what we call our buoyant actuator. That's the prime mover. It's the body that feels the wave and transform that into motion. And that buoy is moored to the seabed with 3 mooring lines. And as it move and pull on these mooring lines, this actuates 3 power takeoff. So the power takeoff is a really crucial component of the technology. It converts that mechanical energy into electrical energy, but also control the force that is being applied in each of the mooring line, and that's really important. So as I mentioned, the electrical power is produced directly inside the buoy and then is exported offshore, onshore with a dynamic export cable. So I'll just play a short video to show you, how the unit behave and what it would look like when deployed in an array. So yeah, you can see the similar design than what I've just shown you with the tree mooring line and the export dynamic cable. I don't know. Okay, so some of the key innovation we've been focusing on, and you know that ties in, I guess, to the evaluation criteria, because they really drive a few of those criteria, like affordability. One of the key innovation we've been pushing hard on is the power takeoff. As I mentioned, it's a critical component, and so we've moved away from you know, our previous version of the technology that was using a linear hydraulic power takeoff to a rotary electric power takeoff. This gives a few advantages. It's a lot more efficient because it's a much more direct. You have less stage in energy conversion. You go directly from mechanical to electrical. You don't have to have those many steps of conversion that you would have with the hydraulic power takeoff. So typically efficiency is higher. Reliability is typically higher as well. You have a lot less parts. You know, it's a bit like the difference between a traditional car and an EV vehicle. There's a lot less maintenance involved, so that drives your reliability of your technology. But probably the most important aspect is that it gives us a much more direct control on the load we can apply on the mooring line, and that's a key enabler of the second important innovation we've been focusing on, which is advanced control. So advanced control is really the ability to react to every single wave that the device that is incoming on the device. So traditional control strategy look at the global sea state that, you know, is being experienced during an hour, and, you know, impose some settings corresponding to the sea state to the power takeoff, and change that every hour or so. This approach is different. It actually adapt and change the force apply by the control system at every single wave. So to do that, we need to have an understanding of what are the waves that are going to be felt by the device in the next couple of wave period. So we've developed a wave predictor, which is composed of an array of wave sensors located upwave of the device, are able to sense the wave and then to predict up to 30 seconds in advance what are going to be the waves felt by the device. And then we have an optimization algorithm that, taking that information into account, is able to predict what is the optimum force to apply right now on the device to extract the most energy as possible. So we've developed two of those algorithms. One that I already mentioned is based on a reinforcement learning approach, and we've done so in collaboration with our friend from HPE Lab. And the second approach is based on the model predictive control, and we've developed this in collaboration with the University of Adelaide. So those type of strategy can yield up to 20% and above of power increase, and so that's why they're so valuable and so important. And we've tested and demonstrated those performance improvements in a recent physical tank testing campaign as part of the EuropeWave project. So now that I've give you a bit of background on the CETO technology and the main innovation related to it, I want to give you some background around the framework in which we're developing that technology at the moment, which is the EuropeWave project. The goal of the project is to advance wave energy converter from the conceptual stage all the way toward commercial exploitation. It's a 65 months program with about 20 million euro of funding, and that has been allocated to the consortium, the buyers group, composed of Wave Energy Scotland, the Spanish Basque Country energy entity, and Ocean Energy Europe. So as Jonathan mentioned, this program runs into 3 phases. There was about 36 submissions to enter phase 1. and 7 of those were retained to progress during phase 1, which is around conceptual development. Then at the end of phase 1, there was an assessment of the result being produced during the phase 1, and also an assessment of the plan that is proposed for phase 2. And 5 companies were selected to progress during phase 2, and that finished in July this year. And now we've just started phase 3, which is a detailed design and the final deployment of the device. So we've been selected together with EDOM and Motion Energy to progress to the third phase of Europewave. So the way the program works is there is actually 3 different locations where the device can be deployed. There is one berth at EMEC, which is a test site in Orkney Island in Scotland, and two berths in BMEP, which is a testing site in Bilbao in the Spanish Basque Country. And because we ranked first in the last phase of the program, we actually got to choose which site we can deploy. And so we're going to deploy at berth number 2 at BMEP, which is our preferred site due to a number of reasons. And I guess these are the different stages of development of the, I guess this is how the Europewave program ties in with the IEA OES framework. So I think Jonathan already touched on that. The Europewave program covers stage 2 and stage 3 of the program. But I guess in more detail, the phase 1, which is a concept development phase of 7 months, is covering the early part of stage 2 of the program, and Europewave phase 2, which is the front-end engineering design and testing, during 9 months covered the later part of stage 2 of the framework. And now we're embarking into both stage 3 and phase 3 of the Europewave program and the IEA framework, which is a detailed design and deployment, which is a 33 months phase. So why are those development stages important? I think Jonathan gave a good justification for that, but I guess maybe a perspective from a developer point of view. And I guess I like to use this graph that's coming from a paper from Joachim Weber, which show I guess the challenge that could be encountered when one develops his technology. So on the horizontal axis, you have the technology readiness level. This is the maturity of the technology. So typically TRL 1, 2, 3 would be, the early concept, maybe just numerical simulation and calculation, early tank testing, so at a really small scale, all the way to TRL 9, which is at TRL 9 you have a full-scale farm, so several units deployed over a long duration. So that's how you can progress, I guess, along that path, and it's related to the stage of development as well of the framework. On the vertical axis, you have the technology performance level. So this is related to how well does your technology perform, and so how do we typically quantify that? Well, it's related mainly to the cost of energy, the LCOE. So the higher your TPL is, the lower your cost of energy is. And so what you can see, those blue dots there, the example that have been selected from, like where developers have been located along the development at different stage. And you can see that a common trend is that perhaps developers tend to prioritize increasing their TRL before they increase their TPL. And that's a challenge, because if you get to TRL 8 or 9 and you realize that your performance, which is your cost of energy, isn't good enough at this stage, that means you're going to need to either go back to a lower TRL to then redemonstrate that, or you have to iterate at high TRL. So you're going to have to iterate doing projects that are involving large-scale deployment that are really expensive. So it's not a cost-effective way at all to develop your technology. A more sensible and more economic way to develop technology that was suggested in this paper is to really focus hard on the performance early on, and to follow this green curve, which at low TRL, when you're doing your conceptual design, your lab test, and your tank testing, you really demonstrate that your technology can perform and can produce a low cost of energy before you embark into doing large-scale development. And this is what really the framework is helping doing, because I guess while you move through this framework, you have to demonstrate that you're following and you're meeting all the evaluation criteria that are described for each phase. So really valuable guidance there for the developers. But I guess, as Jonathan mentioned also as well, the IEA-OES framework, it doesn't work in isolation. It's part of a broader ecosystem which involves standards, so IEC standards and certification body, and the IEC-ERC system as well. So, and I guess from a developer point of view, having this consistent framework is really valuable, because you can really follow it through along the whole way, use the standard, and everything is related. So you're not wasting time trying to analyze, I guess, the difference in terms of language. It's all very consistent. And I guess I just wanted to provide as well a bit of context of how we using this broader context as well of guidance, because we, as part of Europe Wave, we are working in collaboration with certification body Lloyd Register, who are helping us starting our path towards certification. So to get your technology fully certified is a lengthy and complex process, and not necessarily something you want to embark on too early, because you might have to replicate some of the steps if you haven't fully quite got there. But I guess starting that journey early on is really important, and I guess that's what we're doing at the moment with Lloyd's. And what we're doing is we're following a technology qualification process, which is really the first step towards certification. So using the IEC standards, using the guidance from IEA framework. So we're following this process, which is a three-step process of technology verification, technology validation, and performance review as well, which leads to a technology qualification certificate. So we're doing that in a framework of phase 3 of Europe Wave. So now I'd like to talk in more detail about the specific evaluation criteria. So I think Jonathan introduced them already, and I think you've understood that for each stage of development, each of these evaluation criteria are defined, and all the activity you need to do to complete the activity related to that stage of development for these evaluation criteria are detailed really clearly. And I just want to give you a few examples of how we've been going through that process, how we've been, I guess, meeting those evaluation criteria during our Europe Wave project. Apologies, I'm actually using the old 9 evaluation criteria. There is a new one that in the latest edition, which is environmental acceptability. But I won't go through all of them anyway. I'll focus on a few key ones to start with today. So a really important one, obviously, is power capture, which is how much mechanical energy you can extract from the wave and capture with the device. So the way we typically quantify this is we start with numerical simulation. So on the right, you have a bit of a view of a typical numerical simulation there. So and the good thing about numerical simulation is you can iterate a lot. You can run a large number of scenarios which allow you to optimize your design very quickly. But it's typically not sufficient. You always need to validate at some point those numerical validations. So that's what we did by going to tank. So we've done that during phase 1 and during phase 2 of the Europe Wave program. So testing the technology into normal sea state to measure its performance, but also during extreme sea state to check how it behaves against those survival conditions. And then the ability to validate the numerical tool with those measurements is really important. So once you've gathered all of this information, you've validated the model, you can quantify, I guess, your power capture. And that's typically presented by what's called a power matrix, which is how much power do you produce for every typical sea state you would see at a particular site. So, and that's typically characterized with wave height and period of those sea states. Another really important evaluation criteria is power conversion. So we've talked about the mechanical energy we can capture. Now it's about the ability to convert that mechanical energy into electricity and to do so efficiently. So that's the second evaluation criteria. And the way we're doing this is by a combination, again, of numerical simulation and bench testing. So with numerical simulation, we're able to characterize, I guess, how does our power takeoff system behaves and how much time does it spend at different conditions. So this is a plot on the left that shows, the motor torque and the motor speed and what's the percentage of occurrence in those conditions. And then you can relate that to an efficiency map, which gives you, for the corresponding torque and the corresponding speed, what is the efficiency of your system. And from that, you can derive what's your overall efficiency in all conditions. So those type of efficiency map, you typically get them by a combination of kind of supplier information, but also you can do some bench testing to characterize that more accurately as well. So another important evaluation criteria is controllability. So it's your ability to control your system effectively. And the way it's defined in the framework is by different category. Category number 1 being your kind of basic control, which is passive. You set some setting for one sea state and you let the system behave by itself. Category 4, which is what we're targeting, is advanced control, when you react with your system for every single incoming wave, and that requires wave prediction. So I've already talked a bit about that, but I guess that's what we're targeting in that framework, and that's what we've demonstrated in the tank, and will be aiming to also demonstrate during the offshore deployment at BMEP during phase 3. All right, the last criteria I'd like to talk about is reliability. So how do you typically assess and improve the reliability of your system? Well, one of the first steps is to conduct an FMEA, so it's a failure mode and effect analysis. What that is a really big table where you list all your components of your technology, and you list every single way you can think those components could fail and why they failed. Once you've done that, for each of these what's called failure mode, you're going to define what are the probability of occurrence and what's the severity of those failures, which means you can give them a risk score. Once you've done that, you have a really clear visibility on what are the high risk components in your technology. And that's a great tool to then be able to target those components to reduce the inherent risk they have. So that's what we've done, and we've identified amongst a few others the belt, which is one component that convert, I guess, linear motion into rotation. So that belt is wrapping and wrapping on the drum that drive the electrical generator. And we identify that component as a critical component. So we started some testing to fully characterize the belt and ensure that it has the fatigue life we expect, and thus the reliability we expect. Similar story for another component, which is called the mooring tensioner. It's another component of the power takeoff system. It maintains the pretension in the mooring lines, and again, it's a fairly novel component, so we wanted to test it thoroughly, and we've done so with support from the Blue Economy CRC, who's helped us fund a project to develop and test, I guess, this component. So yeah, that's the approach we've been following. I might just complement a little bit on the answer to the question that was asked before about the how the IEA framework capture, I guess, the export cable and the potential challenge that come with it. So in my view, this is addressed in the framework at the moment, because I guess and it is addressed in both power conversion criteria and reliability criteria, because the power conversion is looking at conversion from mechanical energy to electrical energy at your grid connection. So all the export components are included in that assessment. And the same way in the reliability criteria. So the reliability include the reliability of all the components that are used to create and export your energy. So in a way, this is fully included the same way like any other component of the technology would be as well. So I think that's the end of my presentation. I thank you very much for your attention, and happy to take any other question.
Thank you so much, Alex, for your presentation. It's really great to see the success that you're having with your developments of your CETO technology under the EuropeWave project and through your European company as well. So that's absolutely fantastic. Thank you so much. I think maybe some of the people listening might be interested to know what's the timeline for this next phase for Carnegie in developing phase 3 and testing.
Yeah, so as I mentioned, phase 3 start with a detailed design phase with some more bench testing planned for the power takeoff system as well, and after that we're going to move into a manufacturing phase and then a system integration phase, with all of this leading to deployment in early mid 2025. So that's the plan. And then the deployment is actually under the EuropeWave framework is a 1-year deployment. We've recently managed to secure additional funding that allow us to push that deployment to a 2-year duration, which we believe is really important, because we see a lot of demonstration projects that I think we believe 1 year is not sufficient to fully demonstrate all of those evaluation criteria that we've talked about, and the reliability being an important one. So it's a great opportunity to fully demonstrate on a longer duration or technology as well.
Excellent. That's fantastic. We're going to keep an eye on your developments, and I believe that we've been able to today share all the websites so you can hear all about activities that Wave Energy Scotland is involved in, Carnegie Clean Energy is involved in, as well as the Blue Economy CRC. We have had some questions that we've answered, and I really appreciate you, Alex, going back to the question that was asked earlier around the use of the framework for evaluating moorings and other systems as well. So that's great to hear that the framework can be used for that as well. In the Q&A, we've got a couple questions, and I might just start with one of the first questions that's asked. Are you, Alex, and maybe we can start with Jonathan and Alex, are you able to expand on the evaluation criteria for environmental acceptability and any examples of projects that have scored high here?
I can start on that one, Irene. Thanks for the question, Louise. That's an interesting one. We've only added that as a criteria in the last couple of weeks in the new edition of the framework. And the balance of guidance there, I think, is quite interesting because, as I said, the center of knowledge of environmental implications, environmental interactions is the OES environmental group. Those are the people that we're signposting towards for the source of knowledge and the sort of methodologies that should be used here. What we've intended to do with this addition to the OES framework is to very much link, excuse me, the thoughts of environmental acceptability into early stage concept development and early stage concept design, so that people are more aware of the impact that you can have on environmental acceptability of a technology at that early stage with your technology decisions and the characteristics you design in and out of your technology. So we're bringing that thought into the framework to influence early stage technology development. In terms of evaluation criteria, we have pointed people towards the processes of environmental impact assessment and life cycle analysis as the key tools for evaluating the implications through the project, as a way of highlighting the types of characteristics that are important and the types of technical characteristics which are likely have implications for those later stage environmental impacts. So it's not that we're scoring anything against environmental acceptability at this stage, and it will be really interesting to see how funders and technology developers respond to that addition to the framework. So no, I don't have any examples of things that have scored well here, but it's more just bringing it into the thinking at an earlier stage was the intent.
Thanks, Jonathan. Alex, I think from the project that you're doing at the moment, and you're going to be deploying at BitMet, which is at the Basque Energy Clusters test site, what's your position on how you might go about evaluating some of the environmental acceptability criteria, and is that a role that BitMet plays in supporting your project to go there? And how's that work for you?
Maybe just to start with a full disclosure that I haven't been able yet to familiarize myself with this new criteria added to the framework, but nevertheless, environmental acceptability is definitely something we've been, proactive about. Actually, this project funding that allow extension to a 2-year deployment period actually had some environmentability acceptance criteria as well that we had to build our application on. And this is something also we have experience with in our previous deployment. So to give you some example, when we deploy our technology in Perth a couple of years ago, we worked in collaboration with Murdoch University to do some survey to understand, if there was an acoustic impact of a technology, understand the impact on the local fish population. So that's something we've got experience with, and that's something we'll keep doing. And that's something BMEP, as well, as you mentioned, as a test site, has a framework. So to go through the permitting and approval process with BMEP, you have to, I guess, follow this process related to environmental approval, which involves some survey as well, benthic habitat survey, acoustic monitoring as well. So yeah, we're certainly aware of those, and I guess support the need to think early on, when you at the early stage of development, to think about those aspects, because obviously we're there to make a difference to the try to provide sustainable solutions. So the last thing we'd like to do is to create some environmental challenging with our technology. So quite that's something we're quite proactive about.
Wonderful. And there was a question actually from Simon Renwick, who was asking about what scale you'll be testing. So what scale device will you be testing at the event?
Yeah, so we're testing at a scale which is 1 to 2.5. So just to give some further number, the commercial scale CETO has a diameter of 20 meters, and the device will deploy at BMEP has a diameter of 8 meters.
Excellent, thank you.
So
And so, oh, sorry, Alex.
Sorry, no, which is consistent with, I guess, the IEA framework, which prescribe, I guess, the type of range of scale you should be testing at different stage, I guess.
Thanks, Alex. Last question, probably for all of us, is do we offer partnership and collaboration? So I might go to Jonathan Hodges here first, being part of Wave Energy Scotland. How do you engage, and can you engage with other international countries and associations, and what's the best way to do that with Wave Energy Scotland?
Yeah, sure. From a Scottish perspective, so the programs that we've run, the Wave Energy Scotland program and the EuropeWave program, are open to participants from the European Union and the European Free Trade Area. But projects can include partners from all around the world. None of those programs are open to applications at the moment, but keep a look on the websites for updates for future programs which might happen. So it is possible for people around the world to participate. On a more general term, we're always keen to participate, whether it be sharing R&D outcomes, sharing methodologies, experience as a funder, experience of the technology development process, and I guess as the wave energy, developing a wave energy industry and a wave energy market in general. So very happy to collaborate and discuss opportunities on that.
Yeah, and I can speak for the Blue Economy CRC that we have 44 partners, but we engage with just as many third parties. And so we're always open to partnership and collaboration on projects. So very welcome for anyone to reach out to us. Our website provides a lot of information about our current projects and outcomes from those projects, and a look at what we're actually focusing on as well in the future. I'm going to now just, if I can, share my screen. I want to just mention a conference that's actually going to be hosted by the Blue Economy CRC, and that is the International Conference on Ocean Energy. And it is actually the very first time that this event is going to be held in the Southern Hemisphere, and it's going to be held in Australia and New Zealand. And we're bringing together in Melbourne lots of people who are focused on ocean energy. We'll call them our ocean energy leaders, decision makers, researchers from every corner of the globe, for a really rich and exciting program with lots of different sessions, workshops, networking events, and technical visits. Really to give you insights into Oceania and Europe and North America and the Africas, South America, all those activities that are rapidly evolving around ocean energy. I mean, just for some context, in Australia, we've moved to a target of 26% carbon emission reduction to a 43% reduction by 2030. It's very ambitious, and net zero by 2050. Under the Paris Agreement. And, ocean energy sector has a pivotal role to play in this space. And we hope at ICOE 2024 to bring together all those players in the sector to meet this transformational shift. So the event will be held in Melbourne at the Melbourne Exhibition and Convention Centre. It's going to be held in September between the 17th and the 19th, with some tours on the 20th of September. So lots of great information available on the ICOE 2024 website. And just some key dates to keep aware of is that we actually opened very recently with registrations and a call for abstracts. If you're interested to come and present at the conference, please do so. Abstracts will close around the 5th of March. We'll be putting out a preliminary program very early in April. And we'll have options for people to be able to get early bird registrations to keep that cost down for you to attend this conference in Melbourne next year with us. I'm chairing this conference with Christophe Gardin, so we're very pleased to bring this conference, and this is just a little promotional video about the event. Thank you very much. I want to thank our speakers, Jonathan Hodges and Alex Pickard, for their time today and their valuable insights. Your presentations were excellent, and we can see that from all the comments that we've been receiving. Thank you so much to everyone who attended this webinar. If you want a recording of this webinar, it will be available in the coming days on our website. So I want to just say, please just check our website for further information about other future webinars and workshops that are coming up. Thank you so much, everyone, and goodbye.
Thank you, Irene. Thanks, everyone.
Thank you, Irene. Thanks, everyone.